In this chapter, we're going to explore the calculus of exponential and logarithmic functions. In this lesson, we're going to be starting to look at the derivatives of exponential functions.
Okay, hi everybody. So now we're going to take a look at the derivatives of exponential functions, and this is one of my favorite topics to go over with students when I teach calculus here. In fact, this is one of those lessons where even if I was really quite sick, I'd find some way to drag myself in just to go over this with students, because I think what you see here is really kind of special. So what we're going to do here is we're going to take a look at forms or functions of the form f of x is equal to b to the x. Okay. To take the derivative of this, remember, once we start with something brand new, we got to go back to first principles if we're going to take the derivative of it. So remember, f primed of x, using first principles, is going to be the limit as h approaches 0, okay, of f of x plus h minus f of x all over h. Okay, so now we go back and we go to our function here, b to the x. So this is going to be the limit as h approaches 0 of b to the x plus h minus b to the x all over h. Now I'm about to apply a rule here, and let's just glance over to the side here. I want to make sure that you follow along with me here. So let's just take a really quick look at this. If I gave you some sort of function here, let's say it was a to the m multiplied by a to the n. Most people know very quickly, okay, that's just going to be a to the m plus n, which is going to be a to the m multiplied by a to the n. Now, here's the situation that I run into frequently, very frequently. Almost everybody is familiar with this rule here. A to the m, okay, a to the m multiplied by a to the n is equal to a to the m plus n, because you know that if you multiply powers together, you add the exponents. And then when I deal with students, hardly anybody knows this rule. Oh yeah, I've seen that one before, seen that since junior high, I totally get it. Never seen that rule before in my life. Totally. Multiplication becomes addition in the exponent. What? Okay, but it's the same rule. All we're doing here is, instead of it being this constructive thing where we're putting this exponent together, I'm kind of deconstructing the exponent, splitting that up into the two powers that were used to create that value right there. The reason why, or that term right there, I should say, the reason why that's important is because I'm going to apply that right now with this expression right here. And this is going to end up being the limit as h approaches 0 of b to the x multiplied by b to the h minus b to the x all over h. Okay. Now, there's a common factor. Okay, there's a common factor of b to the x there. So I will take b to the x out, and that will leave me with b to the h minus 1 over h. Now, interesting thing about what's going on right here, I am taking the limit as h approaches 0. And notice that that's going to affect this factor, but not this one. So what I can do here is I can actually take that b to the x out and multiply that by the limit as h approaches 0 of b to the h minus 1 over h. And there it is. That is the derivative of b to the x. Now obviously, clearly there needs to be a little bit more said here, but I want to point out a few things here. This is not a fantastic kind of proof of this, but it does kind of really point us nicely in the direction that we need to look here. So what I want you to notice here, first of all, is that b to the x, f of x equals b to the x, the derivative of that is b to the x. Don't lose sight of that little bit right there, b to the x. The derivative of an exponential function is itself, but then multiplied by this piece right here, okay? Now it turns out this limit right here will be unique, okay, for every value of b, okay? Not only that, it turns out that is a number. That is a calculable value, okay? It's a constant. Now, having said that, because that's a constant, notice what this says. Therefore, the derivative, okay, the derivative of an exponential function is itself multiplied by a vertical stretch factor. Oh, my handwriting's getting worse. I'm trying to go faster here. It's being multiplied by, whoa, you can't even see that. It's being multiplied by a vertical stretch factor. This is so cool. The derivative of an exponential function is itself multiplied by some sort of vertical stretch factor. That's a constant. And although it's fairly exciting, it's hard not to get focused on that and think, yeah, but if I've got to figure out what this is every time, not very efficient. How on earth do I even do this? Well, you plug in smaller and smaller values of h, and you see what you get. Okay? So let's take a look at that. In fact, let's take a look at a couple of examples here. So what if we let y equal 2 to the x? And so y primed, I know, has therefore got to be 2 to the x multiplied by the limit as h approaches 0 of 2 to the h minus 1 over h. That's got to be the case. Okay? Now, sorry, I can do this on my calculator. I can play with this a little bit on my calculator. Sure, let me just zoom in a little bit here. I can play with this on my calculator, and in fact, if I do, I'll find out that this particular limit right here is approximately equal to 0.69. Okay, just by plugging smaller and smaller values in for h. Now make sure that if you do this that you're putting parentheses around the numerator, that you're separating the numerator from the denominator, and throwing in smaller and smaller values of h here. So what we get here is that the derivative is roughly equal to 2 to the x multiplied by 0.69. Okay, well, and for those of you that would argue, oh my gosh, is that ever awkward? Yeah, it is. But just hold on. Here we go. Y equals 3 to the x. Okay, so y primed is going to equal, we know this, 3 to the x multiplied by the limit as h approaches 0 of 3 to the h minus 1 over h. I just want to do one more example of this with you here, this one right here. Now, again, I have to go back to my calculator, plug that in, plug in smaller and smaller values, see what happens here, and you get that this is going to be approximately equal to 1.1. Okay, ish. So that means that my derivative here is going to be roughly equal to 3 to the x multiplied by 1.1. Okay, so hopefully you get a sense of what's going on here. Now I'm going to make a few rather sweeping comments about this. Please just kind of take my word that some of these properties hold. Okay, because without going in and spending a lot of time on these things here, there's a couple of ideas that are just amazing that just kind of pop out of this. First of all, I want you to notice, and we can assume this, that as I increase the value of the base here, the value of the limit will also increase. Okay? Just kind of take my word for it. Additionally, that each value of the base, and I've already stated this, but just to come back to it again, each value of that base creates a unique limit here. Now, if that's true, if what I just said that is true there, do you see it? Do you see the property here that makes this so incredible? Now, if you're like me, nope. No, I didn't see it. Okay? And I don't claim to be the one that saw this. In fact, the gentleman that saw this, his name was Leonard Euler. He saw it. And I freely admit and respect and point and admire his genius. If the derivative of 2 to the x is 2 to the x multiplied by some limit, where we use 2 as the base, and we get 0.69. And then the derivative of 3 to the x is equal to 3 to the x, multiplied by some limit, where I use 3 as the base here. And this gets me 0.69, this gets me 1.1. If the value of the limit increases as we increase the base here, okay, and every value of that limit is unique, then it's got to be the case that somewhere in between 2 and 3, there's got to be some number that if I plug it in for the base right here, the limit is equal to 1. It must exist. Okay? There must be a value. Okay? There must be a value between 2 and 3. Okay, so let's say some base here between 2 and 3, such that the limit as h approaches 0 of b to the h minus 1 over h is equal to 1. Now, for that very, very special number, that means, okay, so that being the case, for that base, and just for the moment here, we're going to call that b. We know if y equals b to the x, then it's got to be true that y primed is equal to b to the x. Now we would multiply that now by the limit as h goes to 0 of b to the h minus 1 over h. But we've already established in this particular case, for that particular base, that would be 1. So we've got this function here that exists where it's this exponential function where it is its own derivative. And we call that base, drum roll please, E. E for Euler. Okay, Leonhard Euler here. So the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. That is the defining property of this e right here. Okay, this value e. Now, if you were to go look this up online here, look for the definition of it, you would see that it's slightly different than what I've got expressed right here. It's been reworked here basically to solve for that base. So Leonhard Euler, brings the h over, rearranges this a little bit, but it is the same limit here that we're looking at here. Just to say, if you go online and look it up, it will look different. And that's okay. It's basically just been algebraically rearranged here. Now, that makes, we should probably discuss this. E is approximately equal to, 2.7182812828 ... Now, if you go to your calculator and plug that in, you're going to see that right here. It does look like this is starting to repeat a little bit. You're seeing this thing with the 8s and the 2 in there and whatnot. But actually, it doesn't. It's irrational, okay? It's an element of the irrational numbers. In fact, it's what we call transcendental. I'm not going to get into what that means right now, but it's a very special number. It's like pi, okay? It's like pi in many ways in terms of its properties here. Now, what we know is that now we've got y equals e to the x, okay? And its derivative, y primed, is equal to e to the x. You are going to see from this point on that this is not just an exponential function. Okay, this is not just an exponential function that we can study, although it is. It is an exponential function. It is the exponential function. Okay, when you hear mention of the exponential function, this is what we're referring to. Y equals e to the x. This is so important. This is the one here. In fact, it's got its own three-letter notation here. In fact, it can be written as, and you will see this pop up frequently here, where y is equal to exp to the x. So when you see that, that means exactly the same thing as y equals e to the x. So this is similar to, this is like sine of x, cosine of x, log of x, those sorts of expressions right there, right? But exp to the x, that is the exponential function. Oh, so awesome. Now, having said that and really pointed out how special this is, I want you to recognize, however, it is still an exponential function. And I know it looks like I'm doing some back talk here, but hopefully you'll see what I mean here in a second. It is the exponential function because of the importance that we assign to it. However, I don't want you to lose sight of the fact that it is just an exponential function. So if I've got y equals e to the x, if I graph that, what does it look like? Well, it looks like this. Here, I'll use a different color here. Slides along, then it comes, hits 1, and then goes up. That's what it looks like. It looks like any other exponential function. Okay? In fact, its domain is all reals. Its range, y is greater than 0. X-intercept? Nope. Not unless it's been translated. Y-intercept is just 1. It's got a horizontal asymptote at y is equal to 0. It's just a regular exponential function. But what makes this one unique here is that if I stop and draw a tangent line to it right there, let's call this A, where x is equal to A, the slope of this line is equal to e to the A, which is this point right here, this y-coordinate right there. Its y-coordinate is the slope of the derivative of the tangent line at all points along that curve. It is its own derivative. Now, if you're not really catching why this is so cool, and it really is, I can't oversell this. You will see later on in other math courses that you do here that this exponential function, this e to the x, is like a little Lego block, and you will build more complicated expressions from this. It's a great little tool. It's our go-to when we have exponential growth. In fact, you're going to see, if you've looked at exponential functions before, okay, maybe you've talked about population growth and stuff related to that, you're going to see that a lot of the ways that we normally teach that, before we talk about this, we're sort of stretching things, we're kind of pushing things a little bit just to highlight properties of exponential functions. But e to the x, using e to the x as a model for population growth is a much more natural way of approaching it. Anyway, we will talk a lot more about this over the next couple of videos here. I tell you what, let me take a moment here and let's do some questions. Let's just do some examples where we look at derivatives. Okay, so let's just take a look at some derivatives using the exponential function. And notice I'm not changing the base here. I'm not using a base of b and using that limit as h goes to 0 of b to the h minus 1 over h. Let's just focus on what happens when you've got e. We'll come back around. We'll circle back around and talk about what happens if the base is something different in a bit here. Let's get good at e to the x first. So right here, if y is equal to 5 e to the x, y primed is going to equal, well, remember, don't worry about the coefficient. That's not the issue here. It's the function here, what we're doing to the independent variable. And the derivative of e to the x is just e to the x. So the derivative of 5e to the x would be 5e to the x. Here, 5x e to the x. Well, now I've got two functions here multiplied together. I've got the 5x and I've got the e to the x. So that means I'm going to have to use the product rule. So the derivative of 5x is just going to be 5 multiplied by e to the x, plus the derivative of e to the x is just e to the x. So it'll be 5x e to the x. Okay? Now, normally I would go down here, but I didn't give myself much room. So now what I'm going to do is I'm just going to factor out the common 5e to the x. And that's going to leave me with, from this term here, x plus 1. Okay? Let's do the next one here. 5e to the x squared. Okay, when I take the derivative of this one right here, and we needed to get to this because I need you to see this, that now I've got a function of x in the exponent. Now, first of all, I've got this exponential function to take the derivative of. So 5 times e to some function is going to be 5 times e to some function. That's like the outside part of the chain rule. Now I'm going to move in. This makes a lot more sense if you think about this being written as 5 exp x squared. So the derivative of exp is just going to be exp, it's just going to be the function itself. But now I got to multiply by the derivative of the exponent, which will be 2x. And so just moving things around here, this will become 10x e to the x squared. Okay, so the derivative of the exponential function doesn't change, but I have to include the derivative of the exponent. Now, I suspect there will be a number of you that will look at this and go, oh, why would you do that? But yeah, we got to be prepared for this. I'm just including a trig function here. So notice I've got two functions of x multiplied together. I've got the exponential, I've got the trigonometric. So my derivative is going to be an application of the product rule. Okay, the derivative of e to the negative 2x is going to be e to the negative 2x. It's the exponential function, is the derivative is itself, multiplied by the derivative of the exponent, what's inside. And the derivative of negative 2x is just going to be negative 2. And we'll multiply that by the sine of 3x. And then we'll add to that, okay, e to the negative 2x multiplied by the derivative of sine, which will be cosine, because now we have to take the derivative of the second function here, 3x, and then we'll multiply by the derivative of what's inside. Okay, so now when I take a look at this, what I would likely do with this particular answer here is just factor out the common e to the 2x here. I'll have to do this down here. So e to the negative 2x, and actually because this term has got a negative, I'd probably push that to the end here. So I would make this 3 cosine of 3x minus 2 sine of 3x. Not much else I can do with that right now. Let's take a look at this one. Okay, well, you got to be prepared for something like this. Notice that this one, I've got the y inside there. So when I take the derivative of this, it's got to be implicit. So the derivative of x cubed is just going to be 3x squared, no big deal. The derivative of e to the 5y is still just going to be e to the 5y until I get into the exponent. And that's going to be 5y primed when I take the derivative of that exponent there. Now, to get y primed by itself, I'm just going to divide. So y primed will equal 3x squared divided by 5 e to the 5y. And now finally, just one more here. I'm going to take the derivative, if the function y is equal to e to the x squared, I'm going to take the second derivative, because we can do that again with these sorts of functions here. But it's a bit easier when you're working with the exponential function because the derivative is so easy. So the first derivative of 4e to the x squared is going to be 4e to the x squared multiplied by the derivative of the exponent. The derivative of x squared is 2x. We saw that already. So I'm going to rearrange this a little bit. So this will become 8x e to the x squared. And now when I take the derivative of this, for my second derivative, just note that I've got two functions there. The derivative of 8x will be 8 multiplied by the second function, e to the x squared, plus 8x multiplied by the derivative of that second function. And again, it's exponential, so it's going to be e to the x squared. And then I have to multiply by the derivative of the exponent, which will be, again, 2x. Now I'm going to clean this up. Whoops. I don't know why I wrote that. I'm going to clean this up, make this 8 e to the x squared plus 16x squared e to the x squared. And now I'll take out my common, what have I got here? 8 e to the x squared. And that'll leave me with 1 plus 2x squared. And there's my second derivative. Man, I really love that exponential function. It's so convenient to work with. And it's just going to get better over the next few lessons.